25 trillion miles. That is the width of the abyss between our sun and its nearest stellar neighbor. To a casual observer looking at a cosmic map, it appears as a small gap, a tiny step beyond our solar doorstep. But for human beings and the machines we build, that gap is a graveyard. Pull up the navigation display and lock onto the target, Proxima Centauri. It is a pale red spark, sitting closer to us than any other star in the sky. To visualize that distance, write a 25 in your mind and then follow it with 12 silent zeros. This is the isolation we live in. It is a distance so massive that it shatters human intuition. To understand why we are truly trapped, you have to look past the number and confront the timeline of our failure. Even light, the fastest messenger allowed by the laws of physics, requires 4 years and 3 months just to bridge this void. Think about the lag. A radio signal broadcast from Earth today wouldn't reach a listener at Proxima until a newborn baby on Earth had grown into a school-aged child. And humanity is nowhere near the speed of light. Every vehicle we have ever launched into the dark relies on the primitive logic of burning chemicals. Look at the Saturn V, the Titan of the Apollo era. To move a small capsule just 250,000 miles to our moon, it had to incinerate 3,000 tons of propellant. Proxima Centauri is 100 million times farther than the moon. If you attempt to scale that engineering, the math turns into a nightmare. To reach our nearest neighbor within a single human lifespan using chemical combustion, you would need a fuel reservoir larger than the planet itself. In fact, you would need more fuel than exists in the entire solar system. This is the tyranny of the rocket equation, a mathematical wall that every engineer has hit since the 1950s. Every pound of fuel you add to a ship requires even more fuel just to lift the weight of the propellant itself. It is a self-defeating spiral that ensures no chemical engine will ever leave this cradle. It is why every serious interstellar proposal in history has tried to abandon chemistry. We have designed fusion torches, nuclear pulse drives, and massive sails pushed by the pressure of ground-based lasers. Each of these designs brings us a fraction closer to our goal, but none of them can shatter the ultimate ceiling. That ceiling is the speed of light, roughly 670 million miles per hour. Even at that impossible velocity, Proxima is still a 4-year voyage. At 10% of that speed, it becomes a 42-year sentence in the dark. And yet nothing we have ever built comes anywhere near 1/10 of light speed. Our fastest machines are effectively standing still. Look at the mission profile from a different perspective. If you possessed a craft that could maintain a steady 1% of light speed, and you set out to explore just 1,000 stars in our local neighborhood, your grandchildren's grandchildren would still be drifting in the void long after your original mission brief had expired. The Milky Way spans 100,000 light years. Our immediate cosmic backyard contains hundreds of suns within 20 light years of Earth, but in every practical sense, they might as well be in another universe. They are unreachable. This is the blunt reality that every mission architect must eventually face. Interstellar travel is not an engineering challenge in the way we usually define it. It is a direct confrontation with the sheer, terrifying scale of the vacuum. To make sense of it, cosmologists use metaphors. If you shrivel the entire solar system down to the size of a single US quarter, the nearest star would still be 300 meters away. On that same scale, our galaxy would stretch across the entire United States. There are only 2 exits from this trap. We either build generation ships, metal tombs that drift for 10,000 years while entire civilizations live and die in the corridors without ever seeing a sun, or we find a way to break the speed of light itself. Shift the sensors outward. Currently, 2 machines are drifting into the deep interstellar silence, the fastest objects ever forged by human hands. Voyager 1 and Voyager 2. Launched in 1977 and 2018 respectively, they are the only man-made objects to ever cross the threshold of the heliosphere. Check their speed on the tracking monitor. Voyager 1 is traveling at roughly 38,000 miles per hour. To us, that sounds like a blur. A commercial jet travels at 600 miles per hour. A rifle bullet screams out of the barrel at 2,000. Voyager is moving 19 times faster than a bullet. But when you plug that speed into the Interstellar mission brief, the answer is a crushing disappointment. At 38,000 miles per hour, the trip to Proxima Centauri takes 70,000 years. 70 millennia. To put that in context, 70,000 years ago, modern humans were just beginning to migrate out of Africa. We were sharpening stones and huddling around fires for survival. The invention of agriculture happened only 12,000 years ago. Writing was invented 5,000 years ago. The entire recorded history of our civilization is just a tiny fraction of the time Voyager needs to reach the very first star on our map. And Proxima is our closest neighbor. If the mission target was Sirius, the brightest star in our sky, the trip would consume 150,000 years. If we aimed for the red giant Betelgeuse, our entire species would likely evolve into something else, or go extinct entirely, before the probe ever felt the warmth of that distant sun. The engineers who built the Voyagers were not dreamers, they were realists. They knew these craft would never see another world. The famous golden record, bolted to the side of the probe and filled with the sounds of Earth, was designed to survive for 1 billion years in the vacuum. It was built that way because they knew that is how long these ghosts will need to drift before they ever come near another solar system. Voyager 1 is currently heading toward a star called Gliese 445. In 40,000 years, it will make its closest approach, yet it will still be 1.6 light-years away from that star. A light-year is 6 trillion miles. Passing a star at a distance of nearly 10 trillion miles isn't a visit. It is a silent wave from a vast, cold emptiness. Even our latest record breaker, the Parker Solar Probe, which hit 430,000 miles per hour by diving toward our sun, doesn't change the fundamental math. At that speed, the 70,000-year trip becomes a 7,000-year trip. It is a tenfold improvement, but in the graveyard of space, it is meaningless. You cannot build a bridge to the stars by simply building faster rockets. Every small gain in speed only shaves a single zero off a timeline that is already beyond human reach. You would need to move 10,000 times faster to make interstellar flight practical, and the laws of chemistry refuse to grant us that leap. This is why the architects of the future stopped looking at the engines and started looking at the universe itself. They began to ask, what if the ship doesn't need to move at all? What if space-time could be made to do the work? What if the equations left behind by Albert Einstein already contained a secret trick to move without accelerating? This is the starting point of our briefing. We have to realize that our current path, the path of fire and propulsion, is a dead end. We are floating in a void that is too vast for our biology and too wide for our machines. To reach the stars, we don't need better engineering. We need to find the loophole. We have to understand why the speed limit was built in the first place before we can learn how to dismantle the walls of our cage. And that journey begins in 1905, in the mind of a patent clerk who rewrote the rules of reality. Access the propulsion logs. To understand why we are still confined to this single solar system, you have to understand the fundamental failure of fire. Since the dawn of our species, we have moved by burning things. We burned wood to stay warm, coal to drive locomotives, and eventually liquid hydrogen to reach the moon. But as we look toward the stars, we are hitting a wall that no amount of fire can melt. This is the tyranny of the rocket equation. It is a mathematical trap that was first described by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903, and in over a century of aerospace engineering, we have not found a single way to cheat it. The problem is simple but devastating. To move a mass in space, you must throw something away from you in the opposite direction. This is Newton's third law, In a rocket, that something is exhaust gas. But here is the catch. To move your ship, you need fuel. But that fuel has weight. So now you need more fuel just to carry the weight of the fuel you just added. And then you need even more fuel to carry that weight. In the world of orbital mechanics, this is known as an exponential penalty. For every tiny increase in final velocity, the amount of fuel you need grows at an insane rate. It is why a rocket like the Saturn V was 95% fuel and only 5% ship. We are essentially launching giant, exploding skyscrapers just to put a small tin can into orbit. Look at the fuel mission profile for a trip to Mars. It is our next-door neighbor, a mere stone's throw in the cosmic sense. Even for that short hop, the logistics are a nightmare. To send a crew to Mars and bring them back, you have to launch a massive amount of propellant into Earth's orbit first, or build a rocket so large it beggars belief. Now, take that difficulty and multiply it by a factor of 100 million. That is the jump to Proxima Centauri. If you wanted to accelerate a small, probe-sized spacecraft to just 10% of the speed of light using the most efficient chemical engines we can imagine, you would need a fuel tank larger than the entire observable universe. This isn't an exaggeration. It is a cold, hard consequence of the math. Chemistry is too weak to bridge the stars. It is like trying to reach the moon by building a ladder out of toothpicks. Every mission planner has had to face this brutal reality. It is why our current interstellar probes, like the Voyagers, were never meant to actually arrive anywhere. They were gravity-assisted slingshots, using the momentum of giant planets like Jupiter and Saturn to toss them out of the solar system. They are drifting, not flying. If we want to reach the stars in a time frame that matters to a human life, we need a leap that chemistry cannot provide. Engineers in the 1950s and 60s realized this, leading to projects that sound like science fiction but were terrifyingly real. Project Orion, for example, proposed a ship that would move by dropping nuclear bombs behind it and riding the shockwaves. It was a crude, violent attempt to break the rocket equation through sheer brute force. The math suggested it could work, that it could reach significant fractions of light speed, but it would have left a trail of radioactive fire across the sky. Even if we perfected nuclear fusion rockets or antimatter engines, technologies that are still decades or centuries away, we would still be fighting the same fundamental battle. We would still be carrying our propellant with us. We would still be slaves to the weight of our own energy. This is the emotional weight of the mission. Realizing that as long as we are pushing ourselves through space using any form of internal fuel, we are destined to fail. We are like an ant trying to cross the Atlantic Ocean on a single leaf. No matter how hard the ant paddles, the ocean is simply too vast, and the leaf will rot before it ever sees the other side. But there is a second, even more depressing layer to this trap. Even if you somehow found a way to carry enough fuel, you have to deal with the dead weight problem. In space, there is no friction to stop you, but there is also no way to slow down unless you brought fuel for that too. An interstellar mission isn't just a trip, it's a two-act play. You have to accelerate for half the journey, and then you have to turn the ship around and burn just as much fuel to decelerate so you don't scream past your destination at millions of miles per hour. This doubles your fuel requirement again. The wall just keeps getting higher. Every time we think we found a way over it, the rocket equation adds another zero to the cost. This is why the silence from the stars is so loud. If other civilizations have gone through this same progression, they likely hit the same wall. They realized that burning things, whether it's chemicals, atoms, or antimatter, is a fool's errand for interstellar travel. It is a dead-end technology. It is a local solution for a universal problem. We are a species that has mastered fire, but fire is not enough to leave the cradle. We have spent billions of dollars and decades of research trying to refine a technology that is fundamentally incapable of doing what we ask of it. The realization of this failure is what creates the first great curiosity loop of our mission. If we can't carry our fuel, and we can't burn our way to the stars, then how do we move? The answers started to emerge when we looked at propellant-less propulsion. Ideas like solar sails, which use the pressure of sunlight to push a ship like a boat on the wind. It sounds elegant, but even a sail the size of a city would take centuries to reach the nearest star. It still doesn't crack the real limit. It still doesn't solve the problem of time. The frustration of the rocket equation is what eventually broke the spirits of the old-school engineers and paved the way for the visionaries. They realized that the problem wasn't the engine, it was the entire concept of moving through space. They began to suspect that we were looking at the problem from the wrong side. Instead of trying to push a ship through the vacuum, what if we could make the vacuum do the pushing? What if the leaf didn't need to paddle because the entire ocean was moving in its direction? This shift in perspective is the most dangerous and exciting moment in the history of physics. It requires us to stop thinking of space as an empty room and start thinking of it as a fabric, a material that can be stretched, squeezed, and manipulated. But to do that, we have to face the man who defined that fabric. We have to face Albert Einstein. He is the one who gave us the speed limit, and he is the one who showed us the cage. But as you are about to discover, he also left a set of blueprints that we are only now beginning to understand. Before we can look at the 2024 breakthroughs that finally cracked this cage, we have to understand why the bars were put there in the first place. Why is it that the faster you go, the harder the universe fights back? Why does time itself start to warp when you try to outrun a light beam? The answers are not just academic, they are the keys to our escape. We are moving away from the world of burning fuel and entering a world where geometry is the only engine that matters. Strap in, because to understand how to move spacetime, you first have to understand why Einstein said you can never, ever reach the speed of light. Welcome to the walls of our prison. Welcome to Section 3, Einstein's cage. Open the files labeled 1905. To understand why we are trapped, you have to understand the man who built the walls of our cage. For thousands of years, humans believed that space and time were absolute, a fixed stage upon which the drama of the universe played out. We thought that if you pushed hard enough and long enough, there was no limit to how fast you could go. But a 26-year-old patent clerk in Switzerland changed all of that with a few pages of mathematics. Albert Einstein didn't just discover a law of physics. He discovered a binding contract that the universe has with every piece of matter in existence. And the fine print of that contract is what keeps us from the stars. Look at the fundamental constant, the speed of light, 186,282 miles per second. In our daily lives, speed is relative. If you are on a train moving at 60 miles per hour and you throw a ball forward at 10 miles per hour, an observer on the ground sees that ball moving at 70. This is common sense. But Einstein realized that light plays by a different set of rules. No matter how fast you're moving, a beam of light always passes you at exactly the same speed. If you are in a starship racing at 99% of the speed of light, and you turn on a flashlight, you don't see the beam crawling away from you. It still screams away at 186,000 miles per second. This single baffling fact breaks our reality. For the math to work, for light to remain at a constant speed for everyone, everywhere, forever, something else has to give. That something is space and time themselves. They are not fixed, they are flexible. They stretch and squash to protect the speed of light. This is the birth of relativity, and it is the first bar in our prison cell. As you accelerate toward the light barrier, the universe begins to fight back in a way that feels like a fever dream. Your clocks begin to tick slower than the clocks of those you left behind. Your ship begins to shrink in the direction of motion, and most importantly, your mass begins to increase. Reset the simulation and watch the energy cost. In our primitive world of cars and planes, we assume that more energy always equals more speed. But as you approach the cosmic speed limit, the universe starts converting your kinetic energy into mass. You don't just go faster, you get heavier. At 90% of light speed, your ship is twice as heavy as it was at rest. At 99%, it is 7 times heavier. At 99.9%, the mass of your ship has ballooned by a factor of 22. Now look at the final wall. To reach 100% of the speed of light, your ship's mass would become infinite. And to move an infinite mass, you would need infinite energy. There is not enough energy in all the stars, in all the galaxies, in the entire observable universe to push a single grain of sand to the speed of light. This is not a technological problem. It isn't about building a better engine or finding a more efficient fuel. It is a geometric feature of space-time. The universe has a speed limit built into its very fabric, and we are on the wrong side of it. But the physical wall isn't the most terrifying part of Einstein's cage. The most devastating part is the temporal one. This is the emotional weight of interstellar travel that science fiction often glosses over: time dilation. If you were to somehow build a ship that could cruise at 99% of light speed, and you set out for a star 20 light-years away, the trip might feel like only 3 years to you. You would age 3 years. You would eat 3 years of rations. But when you looked back at Earth through a high-powered telescope, you would see a world you no longer recognize. While 3 years passed for you, 40 years passed for them. Your parents are gone, your friends are elderly. The world you left behind has moved on without you. Interstellar travel under Einstein's rules is a form of one-way time travel. It is a temporal divorce. Every mission to the stars is a funeral for the life you once had. To leave Earth at near light speed is to commit a kind of social suicide. You are not just traveling through space, you are abandoning your place in time. This is the true cruelty of the cage. Even if we found a way to move fast, the universe would punish us by stealing everyone we ever loved. This is why the Fermi paradox, the question of why we haven't seen any aliens, becomes even darker when you look through Einstein's eyes. If every civilization in the galaxy is trapped behind the same wall, then every interstellar traveler is a ghost. Even if they are out there, they are separated by oceans of time that can never be crossed twice. A message sent is a message to a future that the sender will never see. A voyage taken is a permanent goodbye. We are all living in isolated pockets of time, screaming into a void that is too wide for any signal to survive. Mission planners call this causality protection. The universe seems to have a vested interest in keeping different parts of space-time from talking to each other too quickly. If you could travel faster than light, Einstein's math shows that you could, in theory, arrive at your destination before you even left. You could break the sequence of cause and effect. You could kill your own grandfather before you were born. To prevent these logical nightmares, the universe has posted a cosmic guard at the border of 186,000 miles per second. The speed of light is the guard of logic. It ensures that history happens in the right order. So here we are, trapped by mass, trapped by energy, and trapped by time. We are a species with a shelf life of 80 years, trying to navigate a galaxy that demands thousands. We are a species that craves connection, living in a universe that enforces absolute isolation. The bars of the cage are made of the very math that allows us to exist. For over a century, this was the end of the story. Physicists told us to be content with our tiny solar system. They told us that the stars were meant to be looked at, not touched. But look closer at the contract. Einstein said that matter cannot move through space faster than light. He never said that space itself couldn't move. This is the tiny, flickering light at the end of the tunnel. It is a distinction that most people miss, but it is the loophole that changes everything. If you are a passenger on a train, you are limited by the speed of the engine. But what if you aren't on a train? What if you're standing on a piece of ground and the entire continent beneath you is sliding? We have spent 100 years trying to run faster, without realizing that we should have been moving the floor. The cage is real, the walls are thick, and the speed limit is absolute for anything moving inside the room. But in 1994, a physicist realized that the room itself has no speed limit. The fabric of the universe was never part of Einstein's speed trap, and that realization is where the dream of the warp drive was born. Strap in. We are moving away from the world of velocity and entering the world of metric engineering. To escape Einstein's cage, we don't need to break his laws, we need to use them to rewrite the map. We are about to look at the Alcubierre Blueprint, the first real plan to move the stars to us instead of us to the stars. Open the archive labeled May 1994. For nearly 90 years, the walls Einstein built seemed impenetrable. The physics community had accepted their fate. We were a sublight species, destined to live and die in the backyard of a single star. But in a quiet corner of the University of Wales, a young Mexican theoretical physicist named Miguel Alcubierre sat down to solve a problem that most of his colleagues considered a fantasy. He didn't start with a new engine design or an exotic fuel source. He started with a question inspired by an episode of Star Trek. Is it possible to make the math of the warp drive work within the strict, unforgiving laws of general relativity? Alcubierre's realization was a stroke of geometric genius. He understood that Einstein's equations were like a set of rules for a fabric. While the rules strictly forbid any object from moving through that fabric faster than light, they say absolutely nothing about how fast the fabric itself can move. Spacetime is not just an empty stage, it is a physical medium. It can be stretched, squeezed, twisted, and folded. And in the mathematics of the universe, there is no speed limit for the expansion or contraction of space itself. We know this because it has already happened. During the first trillionth of a second after the Big Bang, the universe underwent a period called inflation, where space expanded at speeds far exceeding the speed of light. No laws were broken because no matter was moving, the ground was simply growing. Alcubierre took this cosmic loophole and shrunk it down to the scale of a starship. He proposed a specific metric, a mathematical description of spacetime, that would create what we now call the Alcubierre bubble. Look at the geometry on your display. The concept is as elegant as it is terrifying. The ship sits in the center of a bubble of perfectly flat spacetime. Inside this bubble, everything is normal. Your coffee doesn't spill, your clocks tick at the standard rate, and you feel no sensation of movement. But the wall of the bubble is where the magic happens. On the leading edge of the ship, spacetime is being violently compressed. It is being squeezed into a microscopic point, bringing your destination closer to you. Simultaneously, on the trailing edge of the ship, spacetime is being aggressively expanded, pushing the solar system you just left further away. The ship isn't flying through space, it is riding a wave of geometry. Imagine a surfer on the ocean. The surfer isn't swimming, they are standing perfectly still on their board. It is the wave that provides the velocity. If the wave moves at 100 miles per hour, the surfer moves at 100 miles per hour, even though their muscles aren't doing any work. Alcubierre's ship is the surfer, and the distorted fabric of the universe is the wave. This is the birth of metric engineering. It bypasses every single one of Einstein's barriers. Because the ship is sitting in a pocket of flat space, it never actually accelerates in the traditional sense. It has no inertia, it feels no g-forces. You could go from a standstill to 10 times the speed of light in a fraction of a second, and you wouldn't even feel a jolt in your seat. More importantly, because the ship isn't moving through space, it doesn't gain mass. It doesn't need infinite energy to hit the light barrier, because it never actually hits the barrier. It sidesteps the barrier entirely. Pull up the temporal readout. This is where the Alcubierre design solves the most heartbreaking problem of interstellar travel, time dilation. In Einstein's cage, moving fast means losing your place in time. But in a warp bubble, because you're stationary relative to the space inside your bubble, your clock stays synchronized with the rest of the universe. If you travel to Proxima Centauri at 10 times the speed of light, the trip takes about 5 months. When you return home, 5 months have passed on Earth. Your family is still there. Your life is still waiting for you. The temporal divorce is settled. The Alcubierre Blueprint offered us the galaxy without the cost of our humanity. When this paper was published in the journal Classical and Quantum Gravity, it sent a shockwave through the world of theoretical physics. For the first time, warp drive wasn't just a word used by screenwriters in Hollywood. It was a valid, rigorous solution to the Einstein field equations. The math was checked, rechecked, and verified. It was a physical solution. But as the initial excitement began to settle, the global scientific community began to look at the price tag of this geometric miracle. To manipulate spacetime on such a violent scale, you need a source of gravity that is fundamentally different from anything we have ever touched. Ordinary matter, the atoms in your body, the rocks on a planet, the fire in a sun, curves spacetime inward. This is what we call positive energy, and it creates attractive gravity. But to create an Alcubierre bubble, to expand space behind a ship and push the universe away, you need the opposite. You need negative energy. You need a substance that pushes spacetime outward. You need a form of matter that has never been officially catalogued in the history of human science. This is the exotic matter problem, and it is the moment the Alcubierre dream hit a brick wall. When physicists ran the numbers on how much of this anti-gravity substance would be needed to move a single starship, the answer was beyond comprehension. The original calculations suggested that to build a warp bubble for a small vessel, you would need more negative energy than the total mass of the entire observable universe. It was a mathematical success, but an engineering nightmare. We had found the blueprint for a bridge to the stars, but the bridge had to be built out of a material that didn't seem to exist, in quantities that the universe couldn't provide. But as you are about to see, this was only the first draft. In the world of high-level physics, an impossible energy requirement is often just an invitation to find a more efficient shape. We have spent the last 30 years refining this blueprint, shaving off the energy costs, and looking for loopholes within the loophole. The journey from Alcubierre's observable universe energy requirement to the 2024 physical warp drive is a story of human persistence against the very laws of reality. Strap in, we are leaving the beauty of the geometry and entering the brutal world of exotic matter. To understand how we finally cracked the code, you first have to understand the strange, ghostly substance that Alcubierre's equations demanded. We are going to look at the Casimir effect, the dark secrets of the vacuum, and the reason why nothing might be the most powerful fuel in the galaxy. Welcome to the search for the impossible. Welcome to Section 5, Negative Energy. Open the files on the chemical inventory of the universe. Understand the crisis of the warp drive. You have to understand that we have found the ultimate bridge, but it is locked behind a door that requires a key made of shadows. Every piece of matter you have ever touched, every breath of air you have inhaled, and every star you have seen through a telescope possesses what we call positive energy density. It has mass, it obeys the pull of gravity, and it curves the geometry of spacetime inward, toward itself. This is the fundamental rule of the visible world. But the Alcubierre Blueprint demands a violation of this rule. To expand space behind a ship and push the universe away, you need the mirror image of reality. You need negative energy. Look at the tracking data for exotic matter. This is the term physicists use for a substance that does not exist on our periodic table. It isn't just a rare gas or a heavy metal. It is a substance that would, quite literally, fall upward. If you held a ball of exotic matter in your hand, it would feel like a repulsion, a ghostly pressure trying to escape the Earth's gravitational grip. In the language of general relativity, this matter violates the energy conditions, the set of assumptions that keep the math of the universe sane. Without it, the warp bubble collapses. Without it, the wave of spacetime never forms. The ship sits still, a billion-dollar monument to a fuel we cannot find. The original sin of the 1994 paper was the sheer magnitude of this requirement. When Miguel Alcubierre first calculated how much negative energy was needed to sustain a warp bubble for a small vessel, the answer was a cosmic joke. The equations suggested you would need more energy than exists in the entire observable universe. Even after refinements, the numbers only dropped to the mass energy equivalent of Jupiter. Think about that for a second. To move one human ship to the stars, you would have to take a gas giant, a planet 300 times larger than Earth, and somehow convert its entire physical existence into a form of energy that has never been officially observed in bulk. This wasn't just an engineering problem, it was the economics of the gods. It was a cost so high that it made the dream of the stars feel like a cruel taunt. But why do we think this impossible fuel exists at all? Why didn't the physics community simply laugh Alcubierre out of the room? The answer is hidden in a laboratory bench experiment from 1948. Pull up the records for the Casimir effect. A Dutch physicist named Hendrik Casimir predicted that if you took two perfectly flat, uncharged metal plates and placed them incredibly close together in a vacuum, something strange would happen. They would be pushed together. Not by gravity and not by electromagnetism, but by the vacuum itself. You have to realize that in the world of quantum mechanics, empty space is never actually empty. It is a seething ocean of virtual particles and waves, popping in and out of existence in every trillionth of a second. It is a zero-point field of energy. Casimir realized that by placing two plates extremely close together, shorter than the wavelengths of some of these virtual fluctuations, you could effectively exclude certain waves from the space between the plates. There would be more activity on the outside of the plates than on the inside. This creates a pressure imbalance. The region between the plates becomes less than zero. It becomes a pocket of genuinely negative energy density. In 1997, this effect was finally measured and confirmed in a laboratory. It was the smoking gun. It proved that the universe does, in fact, permit the existence of negative energy. It showed us that nothing is actually something, and that something can be manipulated, but the scale is the tragedy. The amount of negative energy produced in a Casimir experiment is so small it is almost beyond measurement. It is measured in fractions of a trillionth of a joule. To put that in perspective, the energy produced in a lab today is to a warp drive what a single spark from a flint is to the core of a burning sun. We have found the spark, but we are still cavemen staring at it in the dark, wondering how to build the fire. This is the emotional gap in our mission. We know the fuel is real, we can see it, we can measure it, but we have no mechanism to scale it. We are like a civilization that has discovered a single drop of gasoline, but has no way to drill an oil well. The exotic matter problem became the filter through which all warp drive research had to pass. For 20 years, the question wasn't, how do we fly? But how do we pay for the flight? Every paper published after 1994 was a desperate attempt to shave the Jupiter-sized price tag down to something human. Some theorists proposed stacking millions of Casimir plates, trying to harvest the vacuum on an industrial scale. Others looked at squeezed light, a quantum state where the fluctuations of the electromagnetic field are manipulated to create brief spikes of negative energy. But every time we found a loophole, the universe seemed to add a new restriction. Quantum field theory suggests that negative energy is always accompanied by a pulse of positive energy nearby, effectively canceling out the effect over long distances. It's as if the universe has an accounting department that refuses to let us stay in the red for too long. This frustration is what led to the next great pivot in our mission brief. If the fuel is too expensive, the only solution is to redesign the machine. If we cannot find a planet's worth of negative energy, we must build a bubble that is so efficient, so geometrically perfect, that it can run on a fraction of that cost. We had to move away from the brute force physics of Alcubierre and enter the world of torus geometry and thick wall transitions. Strap in, we are moving to the Johnson Space Center. We are going to look at the work of a man who dared to bring the warp drive into a NASA laboratory. We are about to look at the white Alcubierre redesign, the moment we realize that the shape of the bubble is just as important as the fuel inside it. We are about to see how the energy requirement for the stars dropped from the mass of a planet to the weight of a single spacecraft. Welcome to the first real step toward engineering. Welcome to Section 6, Harold White's Hope. Enter the gates of the Johnson Space Center in Houston, Texas. For decades, this has been the heart of human spaceflight, the place where the impossible was made routine. But in a quiet corner of the campus, in a facility known as the Eagleworks Laboratory, a physicist named Harold Sonny White was about to take the Alcubierre Blueprint out of the realm of abstract mathematics and into the world of practical engineering. The year was 2011, and the mission brief was shifting. If we couldn't find a planet's worth of exotic matter, we had to find a way to make the universe's most expensive machine more affordable. White's realization was deceptively simple. He looked at the original Alcubierre metric and noticed a flaw in its design. The wall of the warp bubble was too thin. In the 1994 paper, the transition between the flat space inside the bubble and the flat space outside was mathematically sharp, a razor-thin boundary of intense spacetime curvature. In the world of physics, sharp usually means expensive. The sharper the curve, the more energy you need to maintain it. White proposed a fundamental redesign. He suggested thickening the wall, turning the bubble's edge from a sharp cliff into a soft, gradual slope. Pull up the geometric comparison on your screen. Look at the difference. By widening the transition zone, by making the compression of space in front and the expansion behind more gradual, the energy required to sustain the field began to plummet. But White didn't stop there. He changed the very topology of the bubble. Instead of a perfect sphere, he proposed a torus, a donut-shaped ring of warped spacetime with the ship riding through the center of the hole. This was the aha moment of modern warp theory. The torus geometry concentrated the warping exactly where it was needed and left the rest of the spacetime relatively untouched. When White ran the new numbers through the equations, the result sent a tremor through the aerospace community. The energy requirement, the exotic matter cost, didn't just drop, it disintegrated. The requirement for a human-scale starship went from the mass of the planet Jupiter to roughly 700 kilograms of negative energy. Pause for a second and look at that number. 700 kilograms. That is roughly the weight of the Voyager 1 probe. We went from needing an entire gas giant to needing a mass that we could fit onto a single heavy-duty truck. In the history of theoretical physics, this was a reduction of many trillions of trillions. For the first time, the price tag of the stars was something we could actually wrap our heads around. It transformed the warp drive from a mathematical curiosity of the 21st century into a legitimate engineering roadmap for the 22nd. But Harold White wasn't content with just updating the spreadsheets. He wanted to see if the fabric of the universe would actually bend on command. Access the records for the White-Judy warp field interferometer. This was a laboratory experiment designed to detect the microscopic warping of spacetime. The setup was incredibly sensitive. A laser beam split into two paths, with one path passing through a ring of intense electric fields. The idea was to see if the field would cause a tiny phase shift in the laser, a sign that the geometry of the room had been momentarily altered. The results of the Eagleworks experiments remain one of the most debated chapters in modern propulsion history. White reported anomalous signals, faint, flickering indications that the spacetime within the lab had indeed curved. But the signals were right on the edge of the detector's sensitivity. Critics argued that the results were just noise, thermal fluctuations, vibrations from the street outside, or electromagnetic interference. NASA never officially claimed victory. They never said they had created a warp field, but they didn't say they had failed either. They simply said that the door was ajar. This is the emotional peak of the NASA era, the realization that we were close enough to see the ghost of a warp bubble in a lab in Houston. It gave the field a legitimacy it had never had before. If NASA was funding it, if they were building interferometers to test it, then it wasn't just science fiction anymore. It was pre-frontier research. We were like the Wright brothers, not yet flying, but finally understanding the shape of the wing. However, as the excitement over the 700-kilogram energy budget grew, a different group of physicists began to look at the pilot's perspective of a warp journey. They realized that even if you solved the energy problem, you still had to fly the thing. And that is where the Alcubierre Blueprint revealed its most silent and deadly flaws. We were building a ship that could move faster than light, but we were forgetting that in the universe of Einstein, communication has its own speed limit. Look at the causal diagram for a superluminal bubble. As the ship crosses the light barrier, it creates a horizon on its leading edge. It is a wall of spacetime that moves outward faster than any signal from inside the ship can ever catch it. This means the pilot is causally disconnected from the very bubble they are riding. You can't steer. You can't communicate with the destination. You can't even turn the engines off. The ship becomes a ballistic projectile, a metal coffin screaming through the dark with no way to see what's in front of it. This is the horizon problem, and it is the moment the mission moves from engineering to a struggle for survival. We are about to look at the reality of flying blind. We are going to look at why a warp ship might be the loneliest place in the cosmos, and why the very physics that lets you move might ensure you can never stop. Strap in, we are moving beyond the hope of the laboratory and into the cold, hard logic of the vacuum. We are about to see why reaching the stars is only half the battle, and why the horizon might be the most terrifying thing you'll ever face. Welcome to Section 7, the Horizon Problem. Look at the cockpit displays of a ship that doesn't exist yet. Imagine you are the pilot of the first Alcubierre-class vessel, sitting in a bubble of flat space as the universe outside begins to blur. You have solved the energy problem. You have harvested the negative energy. The ship is stable. You push the throttle forward and the bubble accelerates. Within microseconds, you cross the threshold of 186,000 miles per second. You are now moving faster than light. But at that exact moment, the most terrifying thing in the universe happens. Every screen in front of you goes black. Every sensor reading from the forward arrays drops to zero. Every communication link with the star system ahead of you is severed. You haven't crashed and the ship hasn't failed. You have simply hit the horizon. This is the horizon problem, and in the world of interstellar mission planning, it is the silent killer of the faster-than-light dream. To understand why this happens, you have to look at the very structure of the bubble you are riding. Remember that Einstein's speed limit for light is absolute within any local patch of space. Inside your warp bubble, light still moves at 186,000 miles per second. But the bubble itself, the pocket of geometry you are sitting in, is moving through the outside universe at twice that speed, or 10 times, or 100. This creates a mathematical nightmare called a causal disconnect. Imagine you are standing on the back of a flatbed truck that is moving at 60 miles per hour. If you throw a ball forward at 10 miles per hour, the ball moves away from you. But what happens if the truck is moving at 60 miles per hour and you try to throw a ball forward at only 50? The ball still moves away from you relative to the ground, but it feels like it's fighting to leave your hand. Now take that to the cosmic extreme. If your warp bubble is moving faster than light and you try to send a signal, a beam of light, a radio wave, or even a laser pulse toward the front of the bubble, that signal can never reach the leading edge. The wall of the bubble is moving away from the ship faster than the signal can chase it. Check the causal diagrams on the navigation console. Because no signal from the ship can ever reach the front of the warp field, the pilot has no way to influence the geometry of the bubble once it is moving at superluminal speeds. You cannot adjust the curvature. You cannot steer to avoid an obstacle. You cannot even transmit a message to the destination to tell them you are coming. You are sitting in a causal pocket, a tiny island of reality that has been completely cut off from the universe in front of it. You are effectively flying blind through the most dangerous environment known to man. Think about the emotional weight of that isolation. In a conventional rocket, if you see an asteroid or a debris field, you can fire thrusters and change course. In a warp ship, you are a passenger in a metal coffin with no steering wheel. The bubble is a ballistic projectile. It goes exactly where it was aimed at the moment of launch, and nothing you do inside the cockpit can change its trajectory. If your initial aim was off by even a fraction of a degree, you will scream past your destination star at millions of miles per hour, and you will have no way to pull the brake. This leads to the second, even more disturbing consequence of the horizon. You cannot stop the ship from the inside. To shut down a warp field, you have to be able to manipulate the spacetime geometry at the edge of the bubble. But since you cannot send a signal to that edge, you cannot tell the engines to stop warping space. Once the bubble is moving faster than light, it is a self-sustaining wave that you are trapped inside. Mission planners have joked that the first warp flight will be a one-way trip into infinity, unless someone at the destination can turn the bubble off for you. It is like being on a train with no controls, hoping that someone 1,000 miles away has set the switches correctly. This causality wall is why many physicists believe that faster-than-light travel is a logical impossibility. If you can't control the ship and you can't see where you're going, then the universe has effectively built a firewall around the light barrier. It's as if the cosmos is saying, you can have the speed, but you must give up your agency. We are used to being the masters of our machines. We are used to having a hand on the throttle. But the Alcubierre Blueprint demands a level of surrender that most pilots cannot stomach. You have to commit to a path before you even start the engines, and you have to trust that the math of your launch was perfect, because there are no second chances in the superluminal void. Compare this to the early days of aviation or the first moon missions. Even when things went wrong, the crew had a chance to fight. They had a radio, they had manual overrides, but a warp pilot at 10 times light speed is more isolated than a man buried alive. There is no radio signal in the universe that can catch up to you from behind, and no signal you send can reach anyone in front. You are truly, fundamentally alone in a bubble of flat space, surrounded by a wall of warped geometry that refuses to let information pass. But the horizon isn't just a communication problem, it is a physical furnace. This is the part of the mission briefing that usually stays classified until the final stage. When you create a horizon in spacetime, whether it's the event horizon of a black hole or the leading edge of a warp bubble, you trigger a quantum effect that is as deadly as it is beautiful. You create radiation. Because the vacuum is never empty because it is filled with virtual particles, the presence of a horizon splits these particles apart. One falls into the bubble and the other escapes. This is the Hawking radiation of the warp drive. To the pilot sitting in the cockpit, it doesn't look like a theoretical curiosity. It looks like a lethal stream of high-energy particles pouring through the front window. The very math that allows you to move spacetime also ensures that you are bathed in a temperature that can reach millions of degrees. The horizon isn't just a barrier to your signals. It is a wall of fire that threatens to incinerate the ship and everything inside it before you even reach the halfway point. We are moving away from the problems of steering and entering the world of quantum thermodynamics. We have to look at why a warp bubble is effectively a portable black hole, and why the leading edge of your ship might be the hottest place in the galaxy. We are about to confront the reality of why faster than light might be a death sentence for any biological crew. Strap in, we are entering the heart of the fire. We are going to look at the work of physicists who calculated the temperature of the warp, and why the first superluminal travelers might be cooked alive within seconds. Welcome to the most dangerous chapter of the mission. Welcome to Section 8, the Hawking Radiation Death Trap. Access the thermodynamics report. To understand the next threat, you have to look at the ship not as a vessel of exploration, but as a portable black hole. In 1974, a young Stephen Hawking changed our understanding of the universe by proving that black holes are not perfectly black. He showed that due to quantum effects at the event horizon, black holes must emit a faint, ghostly glow of radiation. This discovery, known as Hawking radiation, is one of the most profound results in modern physics, but for a warp drive pilot, it is a death sentence. Because your ship is moving faster than light, it has created a horizon of its own, and that horizon is about to incinerate you. Look at the thermal sensors on the navigation console. Every vacuum in the universe, even the empty space between stars, is actually a seething sea of quantum fluctuations. Virtual particles are constantly popping into existence in pairs, one matter, one antimatter, and then instantly annihilating each other. This happens billions of times every second, everywhere. But when you introduce an event horizon, the balance is broken. At the leading edge of your warp bubble, space-time is being compressed so violently that it creates a boundary where the rules of cause and effect are severed. When a pair of virtual particles appears on this boundary, one can be trapped inside the bubble while the other escapes into the outside universe. This splitting of particle pairs is the source of the heat. Because the particles can no longer annihilate each other, they become real. The energy for this process is stolen directly from the geometry of the warp field itself. To the outside universe, your ship looks like it is emitting a faint glow, but to the crew sitting inside the bubble, the perspective is horrifying. You are sitting at the receiving end of a continuous, high-energy stream of radiation pouring inward from the front of the bubble. This isn't just light. It is a bombardment of X-rays, gamma rays, and high-velocity particles that are being born from the vacuum and slammed into your hull at relativistic speeds. Now look at the math of the temperature. In the world of black holes, the temperature of Hawking radiation is inversely proportional to the mass. A massive black hole is actually very cold, but a warp bubble is small, and its horizon is extremely tight. When physicists at the University of Sydney ran the calculations for a human-scale warp bubble, the numbers that came back were catastrophic. They found that a superluminal bubble would generate a temperature of thousands, or even millions, of degrees at the leading edge. You aren't just flying a ship, you are sitting inside a furnace that makes the surface of the sun look like a block of ice. Think about the physical reality of this death trap. Within milliseconds of engaging the superluminal drive, the hull of your ship would begin to glow white-hot. Conventional shielding, light, water, or even advanced magnetic fields would be useless. This radiation isn't coming from a distant star, it is being generated by the very spacetime your ship is touching. It is inner radiation. It originates at the boundary of your bubble and moves inward toward the crew. There is nowhere to hide. You would be cooked alive in a matter of heartbeats, your body vaporized into a cloud of atoms before you even realized you had left the solar system. This is the second great filter of the Alcubierre Blueprint. Even if you solve the energy problem with 700 kilograms of negative matter, and even if you find a way to navigate while blind, you are still fighting a war against quantum thermodynamics. The universe seems to have a built-in, self-defense mechanism. It's as if the fabric of space-time hates being warped to such an extreme degree, and it responds by trying to burn the intruder out of existence. The faster you try to go, the hotter the fire becomes. To cross the light barrier is to invite the full fury of the quantum vacuum into your living quarters. Some theorists have suggested that we could pulse the warp drive, turning it on and off so quickly that the heat doesn't have time to build up. But the math of a collapsing and reforming warp bubble is even more unstable. Every time the bubble forms, it creates a shockwave of space-time curvature that could tear the ship apart. Others have proposed shaping the bubble in such a way that the radiation is directed away from the passenger cabin, a geometric heat shield. But so far, no one has found a stable solution that satisfies both the energy requirements and the safety of the crew. The Hawking radiation problem transformed the warp drive from a dream of exploration into a nightmare of engineering. It forced us to realize that we aren't just fighting Einstein's speed limit, we are fighting the fundamental nature of energy itself. We are trying to survive in a regime where the classical world of ships and engines meets the chaotic, violent world of quantum fields. And in that battle, the ship usually loses. It is the ultimate heat wall, a barrier that might be more impenetrable than the speed of light itself. But imagine for a moment that you found a way to survive the fire. Imagine you built a ship out of a material that could withstand the temperature of a sun, or you found a geometric trick to stay cool. You would think that the path to the stars is finally clear. But this is where the mission brief takes its most unexpected and dark turn. Even if you survive the journey, your arrival might be the greatest tragedy in the history of the galaxy. Because a warp bubble isn't just a ship, it is a weapon of mass destruction that you are aiming at your destination. Strap in, we are moving away from the internal dangers of the ship and looking at the external impact on the universe. We are going to look at what happens to the dust, the gas, and the atoms of interstellar space when they get caught in a superluminal wake. We are about to see why a warp ship arriving at Proxima Centauri would be like a nuclear bomb detonating at the heart of the star system. We are about to confront the planet-killer reality of faster-than-light trav. Welcome to Section 9, the planet-killer beam. Look at the sensors monitoring the space ahead of your ship. In our daily lives, we think of the void between stars as a perfect vacuum, a total emptiness where nothing exists. But this is a dangerous misconception. Interstellar space is thinly populated with a ghost-like haze of hydrogen atoms, stray helium nuclei, microscopic grains of silicate dust, and high-energy cosmic rays. The density is incredibly low on average, only one single atom per cubic centimeter of space. To a slow-moving probe like Voyager, this density is a non-factor. The particles simply bounce off the hull or pass through the structure without notice. But when you are riding an Alcubierre bubble at 10 times the speed of light, the emptiness of space becomes your most lethal enemy. You are no longer flying through a vacuum. You are operating a cosmic snowplow that is collecting the energy of 1,000 suns. To understand the planet-killer problem, you have to look at the geometry of the bubble's leading edge. Remember that the front wall of your warp field is a region of space-time that is being violently compressed. As the bubble screams through the interstellar medium at superluminal velocities, it doesn't just pass through the atoms in its path, it sweeps them up. Because the space in front of the ship is contracting, any particle, any stray atom or speck of dust that touches the leading edge gets trapped in the intense gravitational gradient. These particles cannot enter the bubble because of the causal horizon we discussed earlier, and they cannot escape because the bubble is moving faster than they can fly. They become hitchhikers on the wall of your ship's geometry, held in a high-energy reservoir that travels with you across the light years. Think about the physics of this accumulation. Every mile you travel, you are adding more matter to the front of your bubble. Over the 25 trillion miles to Proxima Centauri, your ship will have swept up trillions upon trillions of hydrogen atoms and interstellar dust particles. In any normal context, this would be a negligible amount of mass. But in the context of a warp drive, these particles are being accelerated to apparent kinetic energies that defy human comprehension. Because they are riding on a bubble moving faster than light, these atoms possess more momentum than a fleet of aircraft carriers moving at a fraction of a second. You aren't just carrying dust, you're carrying a concentrated payload of raw kinetic fury. You are building a mass-energy bomb right in front of your cockpit, and the longer your journey lasts, the more devastating that bomb becomes. Now look at the mission brief for the arrival. This is the moment the dream of exploration turns into a galactic tragedy. When you reach Proxima Centauri and prepare to shut down the warp field, you have to decelerate the bubble or collapse the geometry. The moment the warp field vanishes, the reservoir of trapped particles is suddenly released. They are no longer held by the curvature of space-time. They are unleashed into the target star system. Because these particles were traveling at superluminal speeds relative to the destination, they are emitted in a highly concentrated, forward-facing beam of high-energy radiation and relativistic matter. This is the planet-killer beam. The energy release isn't measured in kilotons or megatons. It is measured in solar masses. A warp ship arriving at its destination would unleash a wavefront of gamma rays and high-velocity particles powerful enough to strip the atmosphere off any planet in its path. It would be an event of such colossal violence that it would sterilize every square inch of a target world in a fraction of a second. If there were a civilization living on a planet orbiting Proxima Centauri, they wouldn't see your ship arrive as a peaceful visitor. They would experience your arrival as a cosmic execution. You would show up at their doorstep and accidentally delete their entire biosphere before you even had time to send a greeting. This reality was detailed in a landmark paper in 2012 by a team of physicists at the University of Sydney. They asked a blunt question: what is the environmental impact of a warp ship arrival? Their conclusion was a nightmare for interstellar diplomacy. They found that even a short journey would accumulate enough energy to cause catastrophic damage to anything directly in front of the ship's path. The beam is narrow, focused by the very geometry that allowed you to fly, making it a sniper rifle of pure energy. You cannot arrive gracefully. You cannot show up in orbit and wave. To arrive is to destroy. Every warp ship is, by its very nature, a weapon of mass destruction that cannot be unloaded. Consider the emotional and strategic consequences of this. If an alien civilization detected a warp signature heading toward their star, they would have no way to distinguish between a diplomatic mission and a planetary strike. The physics are identical. The visual signature is the same. In a universe where warp drives are possible, every first contact mission is a declaration of war. You are pointing a loaded howitzer at someone's head and asking for a conversation. This creates a security dilemma on a galactic scale. It might explain why we see no evidence of interstellar traffic. Perhaps any civilization that discovers the math of the warp drive also realizes that using it is an act of supreme aggression. Perhaps the stars are silent because no one wants to accidentally murder their neighbors. Mission planners have looked for workarounds, but every solution introduces a new set of risks. One idea is to aim away, to end the warp journey several billion miles away from the target star, in the empty void of deep space, and let the lethal beam of particles dissipate into nothingness. Then the ship would complete the final leg of the journey using conventional sublight propulsion. It's a logical plan, but it adds years or decades to the mission. It also requires an incredible degree of navigational precision. If you miss your safe exit point by even a few thousand miles, or if the beam doesn't disperse as expected, you still risk incinerating the very world you traveled light years to see. Another proposal is to shape the warp bubble so that it deflects particles instead of trapping them, a kind of aerodynamic smoothing of the spacetime curvature. But the math of a deflecting bubble is exponentially more complex than Alcubierre's original design. It requires even more energy and introduces new instabilities that could cause the bubble to collapse prematurely. For now, the debris problem remains an unsolved barrier. It tells us that the universe doesn't just protect itself through speed limits and radiation, it protects itself through collateral damage. It ensures that anyone who tries to cheat the distance must pay a price that no moral civilization should be willing to pay. Look at the total picture we have built so far. We have a ship that needs a planet's worth of impossible fuel. We have a pilot who is flying blind, causally cut off from the universe. We have a crew that is being cooked by Hawking radiation. And we have a destination that will be obliterated upon our arrival. This was the state of warp drive theory for nearly 30 years. It was a collection of beautiful equations that led to a series of horrifying dead ends. It seemed that the more we learned about the real way to travel faster than light, the more we realized that the universe simply does not want us to leave our home. But this is exactly where the mission brief takes its most revolutionary turn. While the world was focused on the superluminal dream, the quest to break the light barrier, a new group of physicists began to ask a different question. They asked, what if the problem isn't the warp drive itself, but our obsession with going faster than light? What if the loophole Einstein left behind wasn't meant for breaking the speed limit, but for something else entirely? They realized that if you stay asterisk below the speed of light, every single one of these death traps disappears. The Hawking radiation vanishes. The horizon problem evaporates. The planet killer beam never forms. We are moving away from the era of faster-than-light fantasy and entering the era of physical warp engineering. We are about to look at the work of Eric Lentz and the breakthrough framework of 2021. We are going to see how we finally found a way to warp space using nothing but ordinary positive energy. We are about to discover that the stars might still be reachable, not in a heartbeat, but in a way that allows us to survive the trip. Strap in, we are leaving the world of exotic magic behind. We are entering the world of the Soliton. Welcome to the turning point. Welcome to Section 10, the 2021 Soliton shift. Open the 2021 Intelligence Archives. For nearly 3 decades, the dream of interstellar travel had been held hostage by the word unphysical. Every time a physicist sat down to refine Alcubierre's math, they were forced to include a miracle in the equations, a requirement for negative energy that the universe simply refused to provide. The warp drive had become a beautiful mathematical ghost, a bridge made of shadows that no one could actually walk across. But in early 2021, the mission brief underwent its most significant transformation since the 1990s. 2 independent papers, published weeks apart, effectively hit the reset button on the entire field. They moved us away from the era of faster-than-light fantasy and into the era of physical warp engineering. They realized that our obsession with breaking the light barrier was exactly what was keeping us from ever leaving the solar system. The first breakthrough came from the University of Göttingen in Germany. A physicist named Eric Lentz published a paper that challenged the most fundamental assumption of the warp drive, that negative energy was mandatory. Lentz didn't look at the bubble as a simple sphere of curvature. He looked at it as a soliton. In the world of physics, a soliton is a self-reinforcing wave packet that maintains its shape while it travels at constant velocity through a medium. You see them in the ocean, rare, powerful waves that can travel for thousands of miles without flattening out or losing energy. Lentz asked a radical question. Does the geometry of spacetime allow for soliton waves that are made entirely of ordinary positive energy? Access the Soliton diagrams on your display. Look at the shift in the geometry. Lentz found a new class of solutions to Einstein's field equations, shapes of space-time that were more complex than Alcubierre's simple bubble. These designs used hyperfast solitons, waves of curvature that could move at any speed. But the most incredible part of the math was the energy density. By shaping the warp field into a specific, plasma-like configuration, Lentz showed that you could create a warp effect using nothing but classical matter. No exotic shadows, no negative planets, just the kind of energy and mass that actually exists in our periodic table. It was the first time in history that a warp drive had been designed using the same rules that govern a rock, a star, or a human body. But there was a catch, a reality check that the mission brief had to absorb. While Lentz's soliton could theoretically move faster than light, the energy required to reach those speeds was still astronomical. The price tag for superluminal flight remained in the realm of the gods. However, for subluminal speeds just below the light barrier, the energy requirements suddenly looked human. This was the pivot. The physics community realized that a warp drive moving at 99% of light speed was exponentially easier to build than one moving at 101%. By giving up the faster-than-light dream, we had suddenly gained a physical starship. At the same time, a second group of researchers in New York, working under the banner of applied physics, released a framework that would become the Rosetta Stone of the warp drive community. Alexei Bobrik and Gianni Martir published a paper titled Introducing Physical Warp Drives, and it did something no one had done before. It classified every possible warp drive into a single, unified taxonomy. They realized that every design from Alcubierre to White to Lentz followed the same three-region structure. You have the external vacuum of the universe, the internal flat space for the passengers, and the warping shell in between. This framework allowed us to see the mechanical truth of the warp drive. Bobrik and Martir proved that a warp drive is not a magical engine, it is a shell of structured matter. They showed that you could take any mass, a planet, a mountain, or a lead shield, and if you could arrange its density and its motion in a very specific way, it would create a warp effect in its interior. More importantly, they proved a theorem that changed the way we look at propulsion. They showed that a warp drive shell is actually just a form of inertial propulsion. The shell doesn't move itself. It has to be set in motion by a conventional rocket or an external force. The warp drive is the car, but you still need a motor to get the car up to speed. Think about the implications of this 2021 Soliton shift. We had spent decades trying to build a ship that could cheat Einstein's speed limit. We failed because the universe protects that limit with fire and radiation. But the 2021 breakthroughs showed us that we don't need to cheat. A warp drive that moves at 90% of light speed is still the most incredible machine ever conceived. It provides the G-force shielding that allows us to accelerate to insane velocities without crushing the crew. It provides the temporal protection that keeps our clocks in sync with Earth. And it does all of this using ordinary matter that we can actually find and mine. This is the subluminal advantage. By staying below the light barrier, all the death traps we discussed in the previous sections simply disappear. There is no event horizon, so the Hawking radiation never forms. The crew doesn't get cooked. Because there is no causal disconnect, the pilot can steer the ship and communicate with the destination. Because the bubble isn't sweeping up particles at superluminal speeds, the planet killer beam never accumulates. We had been trying to break down the front door of the universe, only to realize that the side door was unlocked all along. We just had to be willing to walk through it a little bit slower. The Bobrik-Martir framework and the Lentz soliton transformed the warp drive from a fringe curiosity into a legitimate engineering discipline. It gave us Warp Factory, the first simulation software that allowed physicists to test their designs on a computer before they ever picked up a wrench. It allowed us to systematically search for the perfect shape of space-time. We were no longer guessing in the dark, we were optimizing. We were looking for a way to bridge the 25 trillion miles to Proxima Centauri without needing to burn a planet for fuel. But even with the 2021 shift, one final hurdle remained. Even a subluminal warp drive still requires an incredible amount of energy to structure the matter shell. We had the blueprint and we had the framework, but we still didn't have the key equation that would make the mass energy requirements small enough for a 21st century civilization to build. We were still looking at energy levels that were out of our reach. That is, until April 2024. We are moving to the final stage of the mission brief. We are going to look at the paper that finally brought everything together, the constant velocity physical warp drive. We are about to see how a team of researchers in 2024 finally found the mathematical configuration that satisfies every single energy condition, uses only ordinary matter, and fits within a realistic energy budget. We are about to look at the real way we will finally leave this solar system. Strap in, this is the moment the graveyard ends and the journey begins. We are going to look at the most important scientific paper of our generation. Welcome to Section 11, the 2024 breakthrough. Reset the mission clock. Access the file labeled April 29, 2024. For 30 years, the dream of the warp drive had been a mathematical ghost, a series of equations that always ended with a requirement for a miracle. Every design we had explored, from Alcubierre's original bubble to Harold White's donut-shaped torus, had a red zone in its sensors, a region of negative energy that defied the laws of the known world. We had the blueprint, but we were missing the ink. But as of 2024, the mission briefing has changed forever. A team of researchers at Applied Physics in New York, led by physicist Jared Fuchs, published a paper in the journal Classical and Quantum Gravity that effectively ended the era of impossible warp drive theory. They didn't just refine the old math, they found the first complete, rigorous, and physically valid solution for a warp drive that requires zero exotic matter. Look at the document on your display, Constant Velocity Physical Warp Drive Solution. This is the culmination of everything we have discussed so far. It is the moment where the miracle was replaced by engineering. The 2024 team did what most physicists thought was impossible. They constructed a warp metric that satisfies every single energy condition known to science. In the world of general relativity, there are four major hurdles: the weak, null, dominant, and strong energy conditions. These are the stability tests of the universe. For 30 years, every warp drive design failed at least one of these tests because they all relied on negative energy densities. But the Fuchs paper shows a design where every single condition is met. No red alerts, no unphysical requirements, no shadows, just ordinary positive energy, the kind of energy found in a rock, a battery, or a human heart. To understand how they did it, you have to look at the matter shell geometry. Pull up the 2024 simulation on your console. The team used their proprietary software, Warp Factory, to scan thousands of possible configurations of spacetime. They realized that the problem with previous designs was that they were trying to warp spacetime from nothing. The 2024 breakthrough treats the warp drive as a dual-layer system. First, you have a shell of structured matter, a physical hull with a specific density profile. Second, you have a shift vector distribution, the mathematical description of how space flows around that hull. By perfectly aligning the gravitational pull of the matter shell with the requirements of the warp field, the team found a sweet spot where the spacetime curves naturally, without the need for anti-gravity or exotic matter. This is a positive energy soliton. It is a wave of spacetime that is held together by its own gravity and the arrangement of its own mass. In the 2024 model, the fuel isn't a mysterious substance from a black hole. It is simply the way you arrange ordinary mass. The paper describes using a high-density plasma-like shell to create the required curvature. This means we are no longer looking for a miracle. We are looking for a manufacturing process. We are moving from the world of what if to the world of how do we build this. The 2024 breakthrough proves that a warp drive is a physical object, a machine that could theoretically be forged in a high-tech facility using the materials we already possess in our solar system. But look closely at the reality readout on your mission brief. There is a reason the headlines in 2024 were a mix of excitement and caution. The Futch solution is explicitly subliminal. It is a constant velocity warp drive that moves at a fixed speed below the speed of light. To a casual observer, this might feel like a defeat. We started this journey looking for a way to break the light barrier, and we have ended up with a machine that stays within it. But this is exactly where the genius of the 2024 paper lies. The team realized that the light barrier is a physical wall for information, but it is not a wall for the warp effect itself. Think about the advantages of a subliminal warp drive. Even at 90% of light speed, you are still traveling faster than anything we have ever launched. But because you are inside a warp bubble, you have the inertial shield. You can accelerate from a standstill to 170,000 miles per second in a heartbeat, and the crew inside would feel zero g-forces. You have solved the problem of human biology. You have solved the temporal divorce because your clocks stay synchronized with Earth. And because you are below the light barrier, you have avoided the Hawking radiation death trap, the steering problems of the causal horizon, and the planet-killing debris beam. The 2024 breakthrough gave us a safe starship. It gave us a craft that can reach Proxima Centauri in 5 years without murdering the crew or destroying the destination. This is the trade-off of the century. We have traded instant travel for possible travel. We have traded science fiction for an engineering roadmap. The authors of the 2024 paper were very clear in their briefing. This design will not deliver the Star Trek future of zipping across the galaxy in days. But it will deliver the interstellar era. It proves that the 25 trillion mile graveyard has a bridge that we can actually build. Jared Futch told the press that the importance of this work is that it shows warped spacetimes are not marginal or impossible solutions. They are a legitimate class of physical objects. We have finally validated the science. Now access the energy budget for the 2024 design. While the exotic matter requirement is gone, the energy required to structure a matter shell remains enormous. To create a warp effect for a human-scale ship, you would still need to manipulate mass energy on a scale that dwarfs our current power grids. We are talking about the energy output of entire nations being concentrated into a single hull. We aren't building this in a backyard garage. We are looking at a civilization-scale project. It will require us to be a Type 1 civilization, one that can harness the total energy of its home planet before we can launch the first physical warp drive. But for the first time in history, we have a target. We have the equations, we have the software, we have the warp factory results showing a clean bubble with no negative energy alerts. The 2024 breakthrough has cleared the debris from our path. It has told us that the universe does allow us to warp its fabric. It has told us that Einstein's laws are not a prison, but a guide. We just had to learn how to read them correctly. We are no longer wandering in the dark, hoping for a miracle. We are now in the development phase. So where does this leave the mission? If we have the 2024 solution, what is the next step? How do we go from a PDF file on a scientist's computer to a hull floating in orbit? This is where the world of simulation meets the world of detection. We are about to look at how we are using Warp Factory to optimize these shells and how we are turning our telescopes toward the stars to see if anyone else has already built what we are just now discovering. We are about to see how we might detect the warp trails of alien civilizations and what the future of our species looks like now that the impossible is officially physical. Strap in, we are moving into the final stages of the brief. We are going to look at the tools that are building our future, and we are going to ask the final question: if we can build it, who else has? Welcome to Section 12, Warp Factory and the Future of Detection. Initialize the Warp Factory interface. Access the numerical simulation logs. To understand the future of the warp drive, you have to understand that we are no longer just dreaming in the dark. We are finally building the tools to see the light. For 30 years, the field of warp physics was a chaotic landscape of disjointed theories and handwritten equations. One physicist would propose a bubble shape. Another would spend years trying to calculate its energy cost. And a third would eventually find a mathematical flaw that invalidated the entire design. There was no standardization, no shared language, and no way to objectively compare one starship design to another. But that era of academic isolation ended with the release of the most important piece of software in the history of interstellar mission planning. This is the Warp Factory. Look at the simulation environment on your main display. Developed by the team at Applied Physics and released as an open-source tool for the global scientific community, Warp Factory is to spacetime engineering what a wind tunnel is to aviation. It is a comprehensive numerical toolkit that allows researchers to input any proposed spacetime metric, any mathematical description of a warp bubble, and instantly evaluate its physical viability. Before this software existed, evaluating a new design was a brutal, months-long process of manual calculus. Now, we can run thousands of iterations in a single afternoon. We are no longer just theorizing about the fabric of the universe, we are stress testing it. We are looking for the structural weaknesses in reality itself. Analyze the visualization readout. When you load a metric into Warp Factory, the software generates a three-dimensional map of the energy density required to sustain that field. It uses a color coding system that has become the red light, green light of the warp drive community. Blue regions represent positive energy, ordinary matter and radiation that we know how to produce. Red regions represent negative energy, the unphysical exotic matter that has haunted this field since 1994. The goal of every modern mission planner is to find a design where the red vanishes entirely. As we saw in the 2024 FUTCH breakthrough, the software finally delivered a blue-only solution. But Warp Factory does more than just check the energy bill. It calculates the momentum flux, the gravitational tidal forces that would act on the crew, and the way light beams would bend as they pass through the bubble's edge. It allows us to walk through the ship before a single atom of the hull is ever forged. This simulation power has created a massive curiosity loop within the physics community. If we can now design physical warp drives on a computer, the question shifted from can we build one to has someone else already done it? This is the birth of the warp drive SETI, a new way to search for extraterrestrial intelligence that doesn't rely on radio waves or optical flashes. For 70 years, we have pointed our telescopes at the stars, listening for a hello in the form of electromagnetic signals. We have heard nothing but silence. But mission planners are now realizing that radio might be a primitive technology that advanced civilizations abandon within a century of its invention. If a civilization has mastered the stars, they aren't using radio to communicate across light years. They are using gravity. And they aren't just sending messages, they are moving ships. Access the gravitational wave detection logs. To understand how we will find them, you have to understand that a warp drive, even a clean one, is a massive disturbance in the fabric of the universe. In Einstein's world, anytime you move a large mass or warp the geometry of space, you create gravitational waves, ripples in the vacuum that travel outward at the speed of light. These ripples are the sound of spacetime bending. In 2015, the LIGO observatories made history by detecting the ripples from two black holes colliding a billion light-years away. It was a faint chirp that lasted a fraction of a second, but a warp drive in operation would produce a signature that is fundamentally different. It wouldn't be a chirp, it would be a hum. Think about the acoustics of the cosmos. A warp bubble traveling at a constant velocity creates a steady, rhythmic distortion of space-time. If an advanced civilization is operating a regular trade route between two star systems, their ships would be emitting a continuous stream of gravitational radiation. This is what mission planners call a warp trail. It is the interstellar equivalent of the wake left behind by a massive ship in the ocean. Even if the alien ship is invisible to our telescopes, even if it emits no light and no heat, it cannot hide its gravitational footprint. The laws of general relativity demand that it leave a trail. Our task now is to build the stethoscopes sensitive enough to hear the heartbeat of a warp-capable galaxy. But there is a catch. The gravitational waves produced by black holes are low frequency, which is why LIGO, with its 4-kilometer-long arms, can detect them. A human-scale warp drive, however, would produce ripples at much higher frequencies, into the kilohertz or even megahertz range. Currently, our detectors are deaf to these frequencies. We are like people trying to listen to a bird's song using a microphone designed for earthquakes. This is why the 2024 mission brief includes a call for a new generation of high-frequency gravitational wave, HFGW, observatories. We are talking about detectors that use superconducting resonators and levitated sensors to pick up the microscopic shimmer of a passing warp bubble. Look at the collapse signature data. This is the most exciting and terrifying part of the detection mission. In 2024, a team led by physicist Katie Clough at Queen Mary University published a study that modeled exactly what happens when a warp drive fails. They used numerical relativity to simulate a warp bubble collapse, a catastrophic event where the geometry of the drive breaks down and the bubble pops. The simulation showed that a collapsing warp drive would release a massive, violent burst of gravitational waves. It would be a cosmic scream that would be detectable across tens of millions of light years. Unlike a black hole merger, which has a specific ring-down pattern, a warp collapse has a unique, high-frequency signature that cannot be mistaken for any other natural event in the universe. This realization has fundamentally changed the search for extraterrestrial intelligence. We are no longer just looking for intent, we are looking for accidents. We are looking for the cosmic equivalent of a plane crash or a ship sinking. If there is a federation of civilizations out there, they might be careful not to broadcast their location via radio, but they cannot prevent the occasional catastrophic failure of a warp field. One single detected collapse event would be enough to prove once and for all that we are not alone. It would give us the frequency of their technology. It would tell us where they are, how big their ships are, and what kind of power levels they are operating at. We would finally have a seat at the table, even if we are only listening to the echoes of their mistakes. Consider the emotional weight of this search. We have spent centuries looking at a silent universe and concluding that we are alone. But what if the universe isn't silent? What if it's loud, and we just haven't been tuned to the right station? What if the space around our solar system is buzzing with the gravitational wakes of thousands of ships, crossing the graveyard at 90% of light speed, while we sit in our cradle, playing with radio toys? The 2024 breakthrough doesn't just give us a way to leave, it gives us a way to see who else has left. It transforms the Fermi paradox from a philosophical mystery into an observational challenge. We aren't asking where are they anymore. We are asking what is the frequency of their warp trail. Analyze the Ramacraft proposal. This is a specific mission plan to use our solar system's own gravity as a lens to detect warp signatures from the other side of the galaxy. By positioning a detector at the solar gravitational lens point, about 550 astronomical units away from the Sun, we could potentially magnify the gravitational ripples of an alien warp drive by a factor of 1 billion. It would be the ultimate deep space radar. We would be able to track every single warp-capable vessel in the Milky Way in real time. We would see the trade routes, the exploration paths, and the migration patterns of an entire galactic civilization. It is a mission that would take decades to launch, but it would provide the most important data in the history of our species. But even as we look outward for alien trails, Warp Factory is forcing us to look inward at our own limitations. The software shows us that while the physical warp drive is mathematically sound, it is an energy hog of the highest order. Even a subliminal bubble requires us to manipulate mass and energy on a scale that current human civilization cannot even begin to grasp. We are like the ancient Greeks having the blueprint for a jet engine. They knew the principles of steam and thrust, but they lacked the metallurgy and the fuel infrastructure to build it. We are in a technological gap. We have the science of the 21st century, but we need the engineering of the 24th. This brings us to the final curiosity loop of our mission. If the science is real and the math is physical, then how do we close the gap? How does a species that still relies on burning fossil fuels and chemical rockets become a species that structures the vacuum of space? The answer lies in the longevity of our civilization. It lies in the realization that the warp drive isn't just a machine, it is a test. It is a test of whether a species can survive long enough to master the energy of its own planet, then its own star, and finally, the geometry of the universe itself. Strap in, we are moving toward the final mission briefing. We are going to look at the long view of the interstellar era. We are going to ask what happens to our society, our biology, and our soul when we finally step into the warp. We are about to confront the reality that the first human to reach Proxima Centauri might already be born, and that the real way to travel faster than light was never about the speed. It was about our willingness to rewrite the definition of what it means to be human. We are leaving the world of simulations and entering the world of destiny. We are about to look at the final chapter of the graveyard. Welcome to Section 13, the future of the species. Close the final archive, look at the timeline of our species. We began as creatures of the dust, huddled around small fires to keep the darkness of the Pleistocene at bay. We looked up at the stars and saw gods, then myths, and finally distant suns. For 300,000 years, we have lived under the assumption that the sky was a beautiful, unreachable ceiling, a masterpiece behind glass that we could admire but never touch. But the mission briefing we have conducted over the last 12 sections tells a different story. It tells us that the glass has a fracture. It tells us that the real way to travel to the stars has finally been mapped, not in the fires of chemistry, but in the cold, elegant logic of geometry. We are standing at the edge of the most significant transition in the history of life on Earth. We are moving from being a planetary species to becoming a cosmic one. And the price of that transition is a total rewriting of what it means to be human. Think about the first individual who will step into a physical warp drive. That person might already be alive. They might be sitting in a classroom today, unaware that their footprints will be the first to mark the soil of a world orbiting a different sun. But as a mission strategist, you have to look past the romanticism and confront the brutal reality of the interstellar epoch. To build the machine we have described, the 2024 constant velocity Soliton, humanity must undergo a metamorphosis. We cannot reach the stars as a divided species, fighting over the dwindling resources of a single planet. Energy requirements alone demand a unified global effort. To structure the vacuum, to forge a matter shell that can withstand the stresses of a warp field, we have to become a Type 1 civilization. We have to master the total energy output of our home world. The warp drive is not just a propulsion system, it is a civilization test. It is the universe's way of ensuring that only those species who have achieved global stability and technological maturity are allowed to leave their cradles. Analyze the biological cost of the journey. Even with the G-force shielding and temporal protection provided by a subluminal warp drive, the stars remain a long-term commitment. A voyage to Proxima Centauri at 90% of light speed is a 5-year mission. A trip to the more distant, potentially habitable exoplanets could take decades. Our biology is fragile, evolved for the specific gravity, radiation levels, and circadian rhythms of Earth. To survive the warp era, we may have to move beyond our natural forms. We are looking at the necessity of directed evolution, the use of CRISPR and cybernetic enhancements to harden our bodies against the rigors of deep space. The humans who arrive at the destination star will not be the same humans who left the Earth. They will be a new branch of the evolutionary tree, a Homo stellaris designed for a life among the suns. We are not just building a ship, we are designing the successors to our own legacy. Consider the ethical weight of the power we are about to unleash. As we discussed in the Planet Killer section, a warp drive is the most destructive weapon ever conceived. The same technology that opens the stars also provides the means to incinerate them. Mastering the warp means mastering the ability to delete a biosphere with a single arrival. This is the dark side of the 2024 breakthrough. Every warp-capable ship is a potential extinction-level event. As a species, we have a poor track record with managing destructive power. We have lived under the shadow of nuclear annihilation for 80 years, and that is a primitive technology compared to the manipulation of spacetime. The future of our species depends on whether our wisdom can grow as fast as our equations. If we step into the warp with the same tribalism and aggression that defined our past, we won't be explorers, we will be a cosmic plague. The universe is a graveyard of many things, and it may well be a graveyard of civilizations that found the loophole but didn't have the soul to use it safely. Now look at the Fermi paradox through the lens of our final conclusion. If the math of the physical warp drive is real and physical, then why is the sky so quiet? Why haven't we seen the warp trails or heard the cosmic screams of failing bubbles from other civilizations? This is the most profound curiosity loop of the mission. Perhaps the energy requirements are so high that most species exhaust their home planet's resources before they ever reach the Type 1 threshold. Perhaps the self-defense mechanisms of the universe, the Hawking radiation and the causal horizons, are barriers that almost no one survives. Or perhaps most chillingly, the physical warp drive is a technology that leads to a great filter. Perhaps every civilization that discovers how to warp space eventually uses that power to destroy itself, leaving nothing but the silent, cold void we see today. But there is a more hopeful possibility. Perhaps the real way to travel faster than light is something we haven't even touched on yet, because it requires a level of consciousness we haven't achieved. Some theorists suggest that the geometry of space and the geometry of mind are linked. That the reason we find the math so difficult is that we are trying to solve it with a brain evolved to hunt and gather, not to fold the universe. The future of the species may involve a cognitive shift, a transition into a post-human intelligence that sees 25 trillion miles not as a distance, but as a thought. We are currently the ants on the leaf, staring at the ocean, but the ants are starting to understand the currents. We are starting to build the tools to measure the salt and the wind. And for the first time in 300,000 years, the ants are looking at the other side of the water and realizing they can get there. Look at the final mission payoff. What do we gain by leaving? It isn't just about resources or finding a planet B, it is about the sovereignty of sentience. As long as we are confined to one planet, one solar system, and one sun, we are vulnerable to a single catastrophic event, a rogue asteroid, a supervolcano, or our own sun's inevitable death. To stay home is to accept an expiration date. To leave is to become indestructible. By spreading across the stars, by establishing outposts in a dozen different systems, humanity ensures that its flame will never be extinguished. We become a permanent feature of the galaxy. We become the architects of the void. The 25 trillion-mile graveyard becomes our playground, and the silence of the universe becomes our conversation. This is the emotional core of the 2024 breakthrough. It isn't about the constant velocity solitons or the shift vector distributions. It is about hope. It is the realization that the universe isn't a prison. It never was. The walls were just an illusion created by our lack of understanding. Einstein didn't build a cage, he just described the terrain. And now we have found the path. We have found the real way. We have moved from the era of impossible to the era of inevitable. The journey will be dangerous. It will be expensive. It will take centuries of focused effort and the total dedication of our species. We will lose ships. We will lose crews. We will make mistakes that will echo across the light years. But we will go. Because the graveyard is too small for us, and the stars have been waiting too long. Strap out, the mission briefing is complete. You have the data on the 25 trillion mile gap. You have the physics of the rocket's failure and the geometry of the warp's success. You have seen the death traps of the horizon and the fire of the vacuum. And you have seen the physical solution of 2024 that finally cleared the way. The navigation console is now in your hands. The future of the species is no longer a question of if, but a question of when. We are the generation that found the loophole. We are the generation that realized the speed of light is not a limit, but a challenge. And as we look up at the night sky tonight, we can finally say, with the full weight of science and the full fire of our souls, we are coming. The graveyard is empty, the stars are open. The mission has only just begun.